All right, we are in Algebra 1. Today's date is Thursday, January 30th. What's going on with my tablets? Having some lag there. There it is. January 30th, 2020. We are simplifying square root expressions, kind of our final segment in our saga of learning about square roots. So our objective today, Wyatt had it again first.
Simplify expressions that have square root.
Yeah, it's as simple as I can get it there. So let's do a bit of review. So if I have the square root of 3 times the square root, or times 5 times the square root of 2 times the square root of 7, I can turn this into what? What am I looking for here on the right hand side? How do I combine? It's kind of like terms. I'm putting quotes around it because it's still like terms. It's just kind of weird to think about. Yeah, Charles?
35 square root 6.
35 square root of 6 is indeed the correct answer. And as an intermediate step, if you're not able to jump right there, is it going to let me grab things? It would be the same thing as, I already have the equal sign, I don't know what I'm writing again. 5 times 7 times square root of 3, I guess it's all under square root of 3 times 2. Yeah, thank you, Charles. So we group some things. I'm looking for some. Yeah, it's one of those guessing games. It starts with an S and then an R for those blanks.
Oh, I thought we were grouping from the thing above.
Oh, yeah. So it's not the most clear. Jay, do you want to take a guess?
Square roots.
Yeah, you're grouping the square roots. And then whatever is left, you group the remainder. So we group the 3 and the 2, the 5 and the 7 was left over, but make sure that you're grouping square roots with square roots and non-square roots with non-square roots. The technical term for these non-square roots is technically degree 1 constants, but you don't need to know that. Or I guess it's degree 0 constants. All right, let's see an example. This is the type of problem that you'll see on Khan Academy. I try to pick 3 different categories. So the first category is like multiplying 2 kind of large guys together, multiplying 3 medium guys together, or 1 giant thing that has 2 different letters, 2 different variables in it. Those are the 3 things that you will see tonight, and you need to be comfortable doing all of them.
So, never. I'm just gonna let you.
All right, so let's do this. So, by Charles's rule, what we should theoretically be doing is we say 6 times 18 to do the inside of the square root. We can all nod our heads, yes, we're going to have to do 6 times 18. But here's the trick. Why, do you already know the trick? Or do you know what 6 times 18 is?
No, I was just saying that there's also variables.
Oh yeah, there's also variables. We're going to deal with all the constants, the numbers first. And are you guys okay with me using the word constant? Whenever I use the word, I'll put it on the notes here on the side, just in case we were confused. Constant is the same thing as if I just say number. So if I say there's a constant of 4, constant of 6, technically a coefficient and a constant of 6, constant, those are all constant terms. All right, so I'm going to deal with the constants, the non-variables first. Question, Charles?
Should we just eliminate the x's first?
We could try to do it doesn't really matter. You could do the variables first or the constants first.
Okay.
I'm going to deal with the constants first because I feel like that's the harder thing. So on the inside of the square root, I'm going to have 6 and 18, but instead of actually multiplying those together, I can just make my factor tree. So off to the right-hand side here, I'm going to say, okay, I don't know what 6 times 8, oh, that's not an 18. 6 times 18 was, but I know that they are some number, and I'm just going to continue the factor tree from there. That's my little trick to you guys. So we don't need to figure out what 6 times 18 is. That's the whole point of the trick, is we can just continue the factor tree. And then I can say, oh yeah, 6 is 2 and 3, 18 is, we'll say 2 and 9, and then 9 is 3 and 3. And I have the ends of the factor tree, which I'm looking for, right? Without having to actually calculate what 6 times 18 is, which is kind of hard. I'm sure we could solve it if we had like 20 seconds. Or a calculator in like 5 seconds. And then from here, we're looking for perfect pairs. Or I have a pair of 2, so doing a pair of 2s like that. I see a pair of 3s right here. And I'm left over with this just 3.
I get it differently. I have 4 3s and 1 2 because I did 6 and 3 for AP.
6. I did.
Two
So
and
6 and 3, and then 3 is 2 and 3. You should have still got 3
Oh, yeah, yeah.
3s and 2 2s.
There you go. Sorry,
Okay.
I did 3 times 3 equals
Yeah.
6.
Yeah.
That's
Otherwise,
okay.
you have broken the fundamental theorem of algebra that there are more than one way to multiply factors together to get a number. All right, so when we have our pairs, we know that whenever we have a pair, that pulls it out of the square root, because essentially what you're saying is the square root of 2 times the square root of 2, or the square root of 4 for this blue area, is 2. So I'm just going to say this is now equal to 2. There's that 2 right there that I just pulled out. I have a pair of 3s, so I'm going to pull out that 3 times 3. I still have the original 4 and 2 as well, so let's write down the 4 times 2 times 4 times 2. All right, and
Mr. Snow, where'd you get the 4 from?
so the 4 came from the original problem. 4 was already a constant term that was pulled out, so there's the constant term. This 2 was already pulled out. These 2 and 3 came from the pairs in our factor tree.
Oh, we need another 3.
Yeah, so I need to give myself some room because I still need to pull out an x too. So give yourself some room. I don't know how many x's I'm going to pull out, but then write your square root off to the right a little bit.
Still there should be 2 X's.
Yes, you already see it. It is going to be x to the power of 2 once we do our work. So over here I'm going to have my leftover 3. So I've dealt with all the constants. I've dealt with all the numbers. Now I need to deal with the variables, and Charles already has the answer for us. He said that it's going to be x to the power of 2, and he is correct.
X to the power of 4 for the constants, and then X to the power of 1.
So you're trying to separate this into x to the power of 4, x to the power of
No.
1, like that?
Well, since you already wait. Oh, never mind. There would just be X to the power of 2 as constants, and then just an X.
Yeah, and technically it's not a constant, it's still a variable. Constant
Well,
just means a number.
Constant as a variable.
So the degree, yeah, the non-square root, I guess.
Well, that's gonna be cool.
So I don't know if you guys are going to be okay if I use a shortcut, but whenever I multiply the same base to a power, I'm using my rules of exponents. So I'm really saying x to the power of 3 plus 2. So this is x to the power of 5. These two multiply together. Does everyone see that this is x to the power of 5? I can skip that step. All right, well, if it's x to the power of 5, and I try to take the square root, I know that 2 is going to come out, because if I divide it by 2, well, I can't divide 5 by 2 because it's a decimal, but I know that the highest number is, the highest exponent is 2. Those words don't mean anything now that I say them out loud. I'm hoping that I can take a shortcut and be like, oh yeah, that's x to the power of 2, and I have x to the power of 1 on the inside. But in the case that you don't see that, let me show you all of the work. This is supposed to be x to the power of 5, because 2 plus 3 is 5. And I don't like leaving x to the power of 5, so I'm going to do some more scratch work off to the side. So my scratch work off to the side, I say, okay, well, the square root of 5, and maybe I'll conserve my space a little bit better. The square root of 5, the square root of x to the power of 5, making so many mistakes today. The square root of x to the power of 5 is equal to the square root of x to the power of 4 times the square root of x. And from there, I know that that's the same thing as x to the power of 2 to the power of 2, and then I'm square rooting that, times the square root of x. And I'll pause there because I feel like I'm going too fast. But if you're feeling like this is easy and I got this, Mr. Sandell, that makes me happy because you know what you're doing. And then from there, whenever I have a square root and a square, they automatically cancel each other out. So I have a square here, a square root. Those are going to cancel each other out. I'm left with x squared on the outside with no square root, and then square root of x on the inside. So I can boil down my final answer now. I have my variables dealt with. I have my constants dealt with. So it's going to be 2 times 2, I'm doing these two first, is 4. 4 times 3 is 12. 12 times 4 is 48. So if someone can back me up, everyone else got 48 as well. 48, and then I have this x squared that I'm going to pull this x squared right over here. 48x squared, and then square root of whatever is remaining. Remember, we have a 3 remaining, so I have a square root of 3, and I have a square root of x remaining, so 3x, and there's my final answer, 48x squared times the square root of 3x. Lots and lots of steps. We're putting everything together. All right. I want you guys to try example 2 on your own. It's a little bit more difficult, but again, you can save some work by making these the branches of your factor tree already without figuring out what 15 times 20 is. See if you can solve example number 2, and if you can't, then you're working with neighbors, you're asking Mr. Sindel for help, and then we'll reconvene after everyone has worked on it for a little bit. All right, volunteers for any parts of the step for example number 2, raise your hand with a card if you have it. Ugo, yes. Yes. Tell me how to do a factor tree.
You put 15 and 20.
15 and 20. All right. 15 is
5 and 3.
perfect. Keep going.
And 5 and 4.
Yep, keep going.
And 2 and 2.
2 and 2. All right.
Why are we still?
I guess you don't have to keep going once you hit a perfect square, right? And then what were the pairs, Ugo? You had a pair of 2s. I see those, and a pair of 5s. All right. Yeah. Thank you. Perfect. All right. So let's go ahead and write out what we have now. Who can do this next step? Once I have my pairs ready. Yeah, Emma.
Write 5 times 2 times 3 times 2.
5 times 2. Those were from our pairs, and then 3 and 2. Those came from our original 3 times 2, our original equation. Perfect. Yeah. Thank you. And now I have the 3 left over, so I'll mark him. The 3 was left over, so that's going to go inside the square root. I'll give myself some room. Square root of 3. And now I have to deal with the fact that I have a bunch of y's. So what do I really have when I'm doing my scratch work? My scratch work over here, I say I really have y to the power of what? And I feel like I have everyone in, right? Eamon, do you have your card? Yeah, I do.
I gave you my card because I thought we were done. So
Oh yeah, go for it.
I'll go. It's y to the power of 12.
Wait, what?
Careful.
No, wrong one. Okay, so y to the power of 8. No, wait, 9.
9, yes.
9, sorry.
Because 5 plus 3 plus this hidden 1 is indeed 9. And did you want to do the next step as well? Y to the power of 9 turns into
Y square root of y to the power of 8 times y.
times the square root of y. Perfect. Did you want to keep going, or do you want to give it to someone else?
I'll give it to someone else.
All right, your choice.
Oh, Yuli has a card.
Oh yeah, Ulysses.
So then we change the y to the 4th in parentheses and into the second, 2.
All right, and then what does that become?
Y 4.
Y to the 4th. Perfect. And I still have the square root of y. So I come back over here and I say, maybe I should change this. I'm trying to color code this better. Let's make all this red. And therefore, when I write in red now, it color codes this to y to the power of 4 and y on the inside. All right, who can give us our final answer? Wyatt.
So I first multiply the 2's to get it on the outside. That'd be 4. 4 times 5 is 20. 20 times 3 is 60.
All
So
right.
60y times y to the power of 4 rooted 3y.
There it is, yeah. I could do a better box.
That was efficient.
So much fun.
All right, any questions on example number 2? All right, and then let's do example number 3 together because I'm worried that we might make some mistakes.
I want to try it on 10.
I multiplied wrong and like
So my first step is to do a factor tree for 48. And because we're starting with the original branch, we can do either method. You can look for perfect squares. 48, so that notoriously difficult one. If you can find the one giant perfect square that goes in there, then you're good. There it is, yep. 48 factor tree, anyone? Charles?
360.
3 and 16. And that's really all you need because it's really the square root of 3 times the square root of 16. And we know what the square root of 16 is, so yeah, I'll write that as 4. And then I have a square root of 3. So 4, and then I'll leave a square root right about there. So I have a 3 right there. So we've dealt with the 48. Killed it. All right, so now we're on to the x to the power of 5, y to the power of 7. I deal with these individually. I do not add their powers. They are separate entities. They are not like terms. In order to be a like term, you have to have the same letter, and these are not the same letter. So I'm going to do some scratch work. So what is the square root of x to the power of 5. That's going to turn into what, which turns into what, which turns into what? It's the same process that we did back here.
Oh.
Charles again?
It would turn into x to the power of 4 times x to the power of 1 in parentheses. Radical. And then it would be x2, 2, and then it would be x2 times 3, 4. No, 4. Sorry.
There it is. So we've now simplified this x to the power of 5 into x squared, square root of x, so then we know which goes where. We have an x squared on the outside, we have an x on the inside, and then finally we deal with this square root of y to the power of 7. Yeah, what?
So first take 1 out of the y to the power of 7, so it would be y to the power of 6, because you want an even number. So then that'd be square root of y. And then you do y to the square root of y to the power of 3 in parentheses to the power of 2. And that would simplify into y to the power of 3 times y square root of 5.
Perfect. And we just put those where they belong, so I'm just going to write the answers.
Okay.
Y to the power of 3 goes there, y goes there, and there's no additional step, there's no additional multiplication, because whenever you have a bunch of variables multiplied together, you just squish them together and you're done. So there's our final answer, box it. And those are the 3 types of problems that you will encounter on the homework.
Thank you, Mr. Chairman.
Yeah.
So,
You may begin on the homework after you give me a fist of 5. How well can you do these types of problems and do this objective?
There's no homework.
Oh, I need to assign that, I guess. 4, 5, 4, 3, 5, 5, and 5. Yeah, those are some nice numbers.